All right, let's get started. Okay, so today we are going to discuss parameter estimation. There are some slides I left over in last lecture. They will reappear in today's lecture, so don't worry that we skip anything. Maybe let me begin with one question. How many of you guys do think the stuff we discuss are too easy? In fact, some of the materials, like the thing we discussed today, did show up before in like 701 other places. If you feel bored, you should let me know. I can skip that. Then how many of you guys thought the stuff we covered too difficult? So it's about right, it sounds like. Okay. Let me know, because we can go infinitely easy or infinitely difficult if depending on your taste. But I do want to adjust the pace based on your needs as much as I can. So today's material looks a lot, but they actually are quite basic and quite easy. I'm going to cover rather fast. And it is to begin with this investigation. We're going to study how to learn graphic models. So in the past few lectures, we talked about, given a graphical model, how can we do inference, right? And now we discuss, given you only the data, how can we obtain the proper graphical model? And the whole setup is like this, right? Of course, we should bear in our mind that we have already named random variables. Okay, turn them from natural name to a notation like A, B, C, D, or X, 1, 2, 3. And then we have a bunch of observations of the instantiation of every node. And learning amounts to the following question. We want to learn the topology of graphical variable dependencies, and also, the parameterizations of the graphic model, which can be a conditional or marginal probabilistic table, or it could be a potential function. And these are very difficult problems. They are still the central theme in machine learning community research. And here I just want to give you a kind of a very high-level view of the landscape. We're not going to actually discuss all of that, but you can see how big the problem can be. So here are some typical scenarios. When we say learning graphic models, we have naturally two paradigms. One is where the graphical model are completely observed, meaning that all the random variables in the domain are totally observed. And of course, they can be directed and undirected graphic models. Okay, so that's a typical scenario. In fact, the difficulty even starts from here. When things are even totally observed, which is rarely true in real life, you can still have a pretty difficult problem if your graphic model is an undirected one. But the directed ones are quite easy. That's the thing we're going to cover today. Then there are another domain which is called partially observed graphic model, in which some of the random variables are not observed. These are the main type of graphic models that we find to be useful. Right? For example, the hidden Markov model is a typical example. You have hidden states. You have observations. You want to use the hidden states to explain the observations. And that's usually even the main purpose of building graphical models, as we will see later. And then in the past, usually we only need to cover these two scenarios using some commonly agreed upon principles. For example, how do we call an estimation to be optimum? Usually, by default, we will say, since we're doing probabilistic graphic model, we should let the model to actually maximize the likelihood of the observation. Therefore, we do maximum likelihood estimation, which is going to be discussed today. But even in the traditional statistical paradigm, there are alternatives, right? You can, for example, choose to perform a Bayesian estimation, which we will also discuss a little bit today. Also, sometimes you can maximize not necessarily the likelihood of the entire data, but the conditional likelihood of some data conditioning on others. So these three are kind of more or less classical. But in recent years, there are actually more principles which turn out to have strong properties in many cases. For example, we learned, in 701, a different type of machine learning model known as support vector machines, right? They seem to be useful for training classifiers. But starting about 10 years ago, people discovered that same principle can be used to estimate first multi-response prediction, structure prediction, sometimes known as. And later, we even discovered that the entire graphical model can be trained to maximize not necessarily likelihood, but the margin. So these are a type of a new estimator we're going to discuss later. And you can also have models which maximize the entropy or the relative entropy of certain certain domain over certain configuration over others, and a combination of max entropy or max margin or many other new ways of forming novel estimators. So these are the now more modern and the more general paradigm of graphical model learning, and we're going to touch bases on some of that. And to summarize, we use the word learning as a name for the process of estimating the parameters in most cases. And sometimes we also use learning to estimate topology. And again, that's a much more difficult problem, and we're going to discuss only a little bit about that. So estimating structure is what people mostly want to do, I have to say. Basically, that means I basically don't need a brain for myself. I can have a machine, and I give them data, and they can discover, anything in the data in terms of dependencies, relationships, and other logical information among random variables. That's really a very, very ambitious but difficult goal for machine learning in general. And such a goal can be achieved in only very limited cases, okay, even though it has been widely studied. And we're going to actually discuss a few cases in our lecture to begin with. Because usually, as I mentioned in our first class, I don't view structured learning as the main goal of machine learning, because it's actually interesting to bring human into loop to provide something as a template so that the other side of the learning problem can be made more rich and more easy to carry out. If you really don't want to do anything, you want the machine to do everything for you, then they can do only very simple stuff. And also there are other statistical issues such as identifiability and interpretability and many other things. So with that reason, I'd like to begin by just giving you some kind of not so good news. So far, there are not too many approaches which allow you to get, probably optimum estimations of graphical model structure. Okay, to my knowledge, there are only maybe two of them. And first of all, let's understand a little bit more. What do we mean by optimum? Some people say, I gave you a graph. Especially this happens in many empirical domains in biology or in other domains. Say, I like this graph. It makes sense to me. They have all this kind of argument telling a graph learned from data makes sense. Or they even show you some validation saying that, a link or a connection learned from data can be experimentally validated. Okay. So those kind of argument can be always found in papers in Nature, Science, and many other scientific journals. Statistically, it is not really a valid argument because what they say is the quality of the true positives. They usually don't examine how many knowledges are there but not discovered by algorithm. So that kind of because what? Because the ground truth is not necessarily available in many cases. Therefore, you must have a kind of independent and more kind of objective measurement of quality. And by that, I mean optimal. Okay, it's actually defined on some loss function, usually a log likelihood or margin or something. And then you call a graph maximizing this score function to be the optimal one. Yeah.
This may seem like a silly question,
the same thing. Structure, topology, graph, they are the same thing.
Okay, so you said that you would only be briefly talking about learning the topology, but it looks like this we are talking about learning the topology of a graph.
Yes.
Is that right?
Yes.
In that case, what I understand, like there's an inherent trade-off between the assumptions that you make in the graph structure and what that implies into the joint distribution. And it looks like when a human being is engineering such a graph structure, it would make sense. But when you want an algorithm to learn this from data, what would it mean to actually tell the algorithm to?
That's why I say we need to actually define a loss function that is qualifying a structure. And usually this graph, this lecture, this class is not about philosophy, say which one we prefer, which one we should prefer. I'm more interested in an engineering approach. Say someone wants to learn a structure that optimizes certain thing. I tell you how to do that. Okay. In terms of which one is better, that debate is endless, and I'm not going to argue for that. Okay. So here I assume that we want to learn a topology which maximizes the log likelihood, and the question is how to do that, how to make that happen. This is a much better defined and crisp problem. And for that, if you look at the early literature, in graphic models, there actually are a lot of algorithms. At that time, they call algorithms, but they actually turn out to be heuristics. Such as structure EM, module network, greedy search of graph, like operators, like added edge, deleted edge, inverted edge, stuff like that. These algorithms had been popular in the past, like a decade or even earlier, but now you don't see them very often. Why? Because they are very, very hard, if possible, to be characterized, and the outcome they deliver can be very arbitrary, depending on who uses it and how you use it. And we are not going to study any of these algorithms, even though they can be published in some good paper. That's just not the goal of this class. Instead, we are going to study these two classes of algorithm for which you are guaranteed to learn a structure, and also it is consistent depending, regardless of who used the algorithm, and they are going to optimize the loss function you set forth for that kind of learning. And one of the algorithms is a very classical one known as the Chow-Liu algorithm. They are good for learning a subclass of graphical models which bear the tree structure, or the graph must be in the family of a tree. And then another class is more modern. It's becoming popular in the past 4 or 5 years, known as a covariance selection or neighborhood selection technique for learning pairwise macro-random field. They can be discrete or continuous. So today we are going to say a few words about the first one. The later one will take an entire class sometime later. All right, so structure search. So again, why actually we have to live in a limited space? Why we don't actually just exhaustively search everything? Well, I guess you can answer this problem quite easily already. How many graphs are there for n nodes? We said that before. It's 2 to the power of n squared, right? Although, it is a little bit more tricky to find out how many trees for n nodes, but the answer is like this. Okay? And this is a much smaller space, still very big, but searching them exhaustively become actually more plausible. But on the other hand, for this particular family of structures, there is actually a very clever algorithm invented in the 60s, which finds you the exact solution of the optimum tree under the maximum likelihood principle. And here are the insights that they make use of. I want to point out before I even present the algorithm. First of all, somehow they actually realized a mapping of this loss function maximum likelihood. Okay. They realized that this score can be decomposed into some summation over edge-related elements. Therefore, this whole score is decomposable, okay, which suggests that you can now turn the whole search procedure into a greedy approach by operating at the unit of edges, because that's basically going to generate loss, addition, or subtraction from the optimal score. That's actually one important insight. The other is also that search the tree space is easy because every node has only one parent in the search space. Therefore, if you have the search strategy, done right, you actually can systematically exhaust the whole space without experience a exponential explosion of the complexity. Okay, so this algorithm is known as the Chow-Liu algorithm. So let's study, the first element, how the loss function become decomposable. Okay, it's a slightly tricky kind of transformation, and let's go through them slowly. So, what is a loss function? Based on likelihood over data. So here is the joint likelihood, right? We define the probability, the likelihood of data given two things: the graph and also the parameters defined on the graph. Okay, and using the BaseNet factorization rule, we can now decompose that into this product. Anybody should recognize that, right? In the inner product, this is the base network factorization. You are going to traverse over all the nodes, multiply everything, which is a node given their parent. It's a conditional probability distribution. Okay, and then this one is to multiply over n pieces of data. You actually observe n instances of that. So this defines the joint likelihood. And of course, you have a logarithm outside, which turn the multiplication into summation, and we have that. So from here to here, you notice I did one thing. Okay, I exchanged the ordering of n and I, which doesn't hurt the result. Okay, that's the first tricky step. And then this basically means for every node, I'm going to examine that log likelihood of the node conditional probability over all instances of my data set. Okay? So that's the first kind of transformation. And then I'm going to do another transformation. So here, I'm basically counting, this instantiation of the node and its parent over all the data instances. Okay? Here, I'm redoing the counting. I'm going to actually count not over instances. I'm going to count over different instantiations or different values that this node and their parent can take. And I count how many times each configuration happened in my data set. Okay, so these two counting procedures are equivalent. Okay, but the kind of the analytical form look a little bit different. Okay, so sum over data points now become sum over counts of variable states. Okay, and that's actually an important thing for me to now turn this quantity into a empirical estimation of the conditional probability, because these are counts and relative counts and total counts. Okay, therefore I can rewrite this into my empirical probability of the joint configuration of the node and their parents. Yeah.
So here we are assuming that the graph structure is known, but isn't that what we're trying to learn?
The graph structure is not known. Did I say any structure in here? I'm basically generically saying this is a placeholder of some structure. Okay, any structure can be presented in this way, right? Okay, so now we have this log likelihood now becomes this guy, which is a log conditional probability times the joint probability of the child and the parent on the outside. And then I'm going to define my loss function only over data. Therefore, this whole thing becomes a sample probability. Okay, so I have this little hat there. And that basically turns this part also into a p hat. Okay, so now look at this. This term is what I copied from the first slice. And then you can do some additional massage. You introduce in here, you basically now redefine, just by definition, write this as the marginal divided by the marginal of the child and parent divided by the marginal of the parent. And then here you put denominator and numerator to be both having a component of p over xi, which is the marginal of the child. And why that's interesting? Well, now I can actually write some tricky kind of reorganization. So if you bring this part together, okay, and without going through the definition of the mutual information, actually this part can be written together, and they define the empirical estimation of the mutual information between a node and their parent. Okay, and the residual, which what is left is this part and that part. Okay, that part actually because it is sum over both the parent and the node, and in the argument of the summand there isn't any parent. Therefore, that one gets marginalized. Therefore, you have only this part left. Therefore, you have the entropy of every parent. Okay. So now, with some massaging, we have now this new definition of the likelihood, okay, of the data, which now is defined in terms of mutual information and entropy. Okay. Okay. So now let's see what should we move. Remember here, I don't know the graph yet. This decomposition is general for all possible graphs. The graph is in here. Basically, every node will have some parents, and the graph topology decides who their parents are. Okay, and now we need to learn the graph, which means that out of n minus 1 possible nodes, which one is a parent, or which several are the parents of this node I for every I. Okay. All right. And we can further simplify the loss function a little bit as a function of the graph topology, because this guy is a single node entropy function. There is no structural information encoded here. Okay, we can ignore that. Therefore, the cost or the loss function of a graph is solely dependent on the sum of mutual information between a node and their parents. Okay, and that comes to the Chow-Liu algorithm. Okay. First, Chow-Liu assumes that we only care about a tree structure. Therefore, every node had only one parent. Okay. So you have this reduction that this guy actually can be written as a mutual information between any pair of nodes. Okay. And secondly, computing the mutual information between a pair of nodes, we should know that very well, right? Basically, they are the counts of a pair divided by the the counts of every singleton and up to this definition. So you can compute empirical mutual information as directly from the data for every pair of nodes. Okay. So basically, you can pre-compute this based on data for every pair of nodes, and then you basically have the information for all possible parents of a particular node. And then what you do is to basically define, a graph which maximizes this particular quantity. And what does that operation correspond to? If the graph is a tree. It is a maximum spanning tree, because you can basically view in the tree every edge had a score which corresponds to this mutual information. And then if you find the tree which has the maximum spanning, then you basically have the maximum likelihood estimation of that tree structure. Okay, so there's nothing new. You only need to know how to compute from the data mutual information based on these two equations. And then you need to know a maximum spanning tree algorithm, like a Dijkstrom algorithm or any other algorithms. Okay, so that basically gives you the optimum Bayesian network. And it is guaranteed to reach optimality after you finish this procedure. Yeah?
Sorry, just to be clear, that only works on trees because
only works on trees.
Information is only defined between single nodes?
Yes.
Or
a pair of nodes.
Between pair of nodes. So
yeah.
Is there a measure of visual information between a node and a set of nodes?
You can define, yeah. You can of course define, two parents. You can still mutual information well defined, but the matter is that how can you afford to compute it? This one is a n-square algorithm, a quadratic algorithm. And if you want to define more parents, you need to, again, do all this pre-computing, right? And also, the topology become a little bit obscure. If you have 2 parents or more, and how do you actually define a maximizing topology, which is, searchable, or attainable in a polynomial time? That's another question. Yeah.
So mutual information is a symmetric relationship.
Mm-hmm. Yeah.
Given the fact that it's symmetric,
Mm-hmm.
how do you get a Bayesian network where you have directed edges? Because you could equally have the opposite edge and...
That's a good question. Remember, in Bayesian network, we talk about the limitation of the identifiability of a topology in a graphical model, right? Basically, in a tree Bayesian network, no matter how you hand the tree, okay, which one to be the root, they give you different trees but with the same likelihood function. Okay, that's actually exactly what I'm trying to say here. There are many I-equivalent graphs, okay, which give you the same likelihood. Okay, so that's why it is a Bayesian network, but it is not a unique Bayesian network. Okay, and that's actually one of the strong reasons that I'm against using this technique to find semantically meaningful topology. Say you want to explain a phenomenon. Okay, this tree and this tree are equivalent in the maxi likelihood sense, but they have totally different meaning. Therefore, why do you favor one meaning over the other? There's no reason. Okay. So many amateur machine learning people feel like they want to use this to learn an optimum tree, which afterwards they will tell a story with this tree. And as statistician or as machine learning guys, you should reject this kind of temptation. It is not right. Okay. So then we'll say, why should we care about this? Well, I would say this gives you an interesting density function or joint distribution of multivariate distribution. Okay. Instead of having a gigantic table, you have all this, very economical parameterization of the whole model. In terms of how meaningful they are, well, they are meaningful in the limit of I equivalence. Okay. Yeah.
So we cannot apply this algorithm to the graph with latent variables.
No. Okay. All right. Any question? That's actually an algorithm I want you to remember. Because, for example, I can give you one application scene here. There are, one of the papers, I think I could put it there, written by one of my colleagues, Marilla Miller from UW, was to make a prediction on whether a sequence of DNA belongs to a promoter or some other junk sequence. Okay, a sequence basically is, a linear kind of chain of many random variables, and each one is a particular DNA site. And what she did is, I want to build a model to write down the joint distribution of this whole thing, and conditioning on whether it is a meaningful sequence like a motif, regulator unit, or it is a background sequence. I may have different likelihood. The question is that how do we parameterize this likelihood function? Okay, you can write the giant table of this whole long sequence, which is not very good. You can also have maybe a Markov chain to prefer this order to that order to write a sequence of products. Not quite good either, because that's having strong assumptions on the dependencies between different characters. So what she proposed is to learn a tree out of all these nodes, because these different nodes, even though they are in a chain, they can be dependent statistically or biologically in arbitrary way, which they don't know. Not necessarily causal, but correlational maybe. Maybe here this pair is connected, this pair is connected. She chose to use a tree to capture that. So that's basically a tree density estimation of this multivariate data. And then she was able to learn 2 trees. One is a tree corresponding to motif. The other is corresponding to the background. Then you can differentiate using that as a classifier, okay, and to actually classify sequence labels. That's a typical application. But on the other hand, she did not attempt to use the learned tree to tell a story about how these nodes are biologically actually depending on each other. That's just a statistical representation of the density. Biologists probably would be very excited about this tree and try to tell a story. I have to say I don't believe that, okay, because there is a statistical equivalence among all these possible configurations. All right, any other questions before I move on? Yeah.
What if there is a limit variable?
Then you declare, I don't know how to do it. There are limitations in this model. You do something else. Yeah. This kind of question can all be there. What if I have a trailing random variable? I can ask that. Then I will say, I don't know. Right. So that's an open question, and we have some ideas once we are into spectrum graphic models later on. But once you have latent variables, you lose the guarantee of learning the optimal model. Okay. All right. So here's a theorem claiming the correctness of that, and I also have some comments on other heuristics being existent but incorrect. All right. With that, I'm going to move on to very quickly a quick survey of methods for parameter estimation, assuming that everything is observed and the structure is given. Okay. So the general idea is the same, is what you see before, right? We have all this data. We make an important assumption that data are IID, meaning that all these data are coming from the same distribution that we want to estimate, so that we can write down the log likelihood as this form. Okay, it's the sum of log likelihood and the sum of log likelihood over every building blocks in the graphical model. Okay. And of course, here I want you to pay attention to these notations. Here we have an index for the data points, and here we have another index for the dimension in the data. Therefore, it is a collection of multivariate random vectors. And so how do we start? Remember that the reason for preferring a graphical model over a tabular big parameterization is that the graphical model makes the joint decomposable into small pieces, right? And each of the piece is a function of a local parameter, theta I, which only cares about the local configuration of involving I and their parents. Okay, you can have the equivalent argument if you use indirect graphical model. So all we need to know is to actually learn how to estimate this for every small piece. The smallest piece is just a single random variable, which is just the parent, the root of a graphical model. And remember in last lecture, we said that there are canonical ways of parameterizing that. This is equivalent to a density estimation, right? And the kind of densities that we use to play with are all members of an exponential family distribution. In a sense, we have a generic way of estimating the parameter using, if someone can remember me, what is that? We can do moment matching, right? To basically collect a sufficient statistic and then directly estimate the mean parameters. And then there is a deterministic transformation from the mean parameters to the natural parameters, so we get that as well. So in a sense, we are done with this already, but I want to go through a few examples so that you can remember the typical practice. In particular, there are different Bayesian priors defined for different choices of the density, so that one can get smooth estimation or Bayesian estimation with informed prior knowledges. And remember, this is one of the building blocks of a general graphical model. So we are going to discuss a few instances for discrete distributions, and here is an example of such a discrete distributions. And one is a binary discrete random variable. You can also have a multi-way discrete random variable. And remember, our way of parameterizing such variable is through a random vector, okay, in which every element can be either 0 and 1, and therefore the value of an outcome is not described by a number 1, 2, 3, 4, 5, 6. It is defined by a vector of indicator functions. Anybody want to remind the class why this is a favored representation over a numerical one-dimensional scalar? comments? I think we should discuss that in 701 before. This is kind of cumbersome, right? A simple outcome of 6 should now take the value of 0, 0, 0, 0, 0, 1. Kind of cumbersome. Why don't I just call x equals to 6? Any insight?
It's a mathematical convenience. We can, when we multiply, it's easier. It's a mathematical convenience to just have a function which indicates the value at a certain state.
I see what you mean. So basically, we are avoiding, basically attributing events with a numerical interpretation. Okay, 6. What if I call this any other name? Maybe in the English word there are people's name, and then I'm going to say x equal to a chair. And how do we average a chair and a table? Right. So taking manipulations out of these indexers are not very interesting. They are actually quite misleading. But this one basically is an event indicator. Okay, they are basically saying which event happens or not, and whether it is taking a value of 6 or 5 doesn't matter. We can call this north, east, west, and south, and up and down, something like that. They also give me 6 configurations. And then when you later on collapse all data, taking averages, you're not going to get something strange like a 2.5, which is not even an existent event. You are going to get a vector of frequencies. Okay, so that's kind of the insight. I want you to go over and reflect on that. And similarly, we have multiple distribution for word indicators and stuff like that. And the type of distribution we use is called a multinomial distribution. Again, I'm going to just quickly flash at you the slides, and you should go home and figure out the definition by yourself, because we went into that before. So basically, what you do is to write down the data likelihood, okay? And it is important to realize now that the data likelihood should be a function of the unknown parameter theta and the realization of the random variable, okay? They jointly define the likelihood of the event. And if you have multiple data, you multiply them together. And then here is your likelihood function. And thanks to the definition of the format of our variable, we are going to now have this argument to capture the actual observations in the data. And they can be summarized into sufficient statistic as the event of certain thing happens. Right? And again, this is a particular instance of a expanded family distribution. And then how to estimate theta. The general kind of roadmap is that you have this loss function, which is now the function of the data set and the function of the unknown parameter. You are going to take a derivative, of that loss function to whatever things you want to estimate, set them to 0. And then you compute, the number, the estimator from that derivation. Here, there is one thing I want you to be careful about, which is these numbers are not free, actually arbitrary numbers. Okay, in particular, these theta are probabilistic probability numbers. Therefore, they have to be positive and they have to sum to 1. Therefore, there are constraints. And how do we bring constraint into an estimation? We use a Lagrange multiplier to produce a Lagrangian. So that's where you have here. And then at the end of the day, you get something you expect, which is that the estimated probability of an event is the sample frequency of that event. So these equations basically tells you what the intuitive outcome was actually formally derived. Okay. But this roadmap is pretty general. Down the road, if you are playing with an unknown distribution, you pretty much should follow the same procedure even if you don't know the final outcome. You basically bring in the constraint and you write down the loss itself, you take your derivative, and then you get either an analytical or a updated equation of your parameter estimation. All right. And now maybe we can spend a few words about the Bayesian estimation. Bayesian estimation means that I have some prior knowledge about the parameters that I have. This theta is a vector of probabilities. Every event can happen. And now I assume that I even have some prior information about how such probabilities are distributed. And here is a typical prior distribution known as the Dirichlet. Okay, if you plot the density, this is a three-dimensional Dirichlet distribution. You can see the density is roughly like this, or something like this. The shape of the density depends on how you actually put values at here, which are called the hyperparameters. These alphas are hyperparameters. Okay, and then there is this kind of a mysterious normalization constant, C alpha, which can be also calculated analytically. It is a gamma function over the alpha. And then once you have the prior, your posterior is now defined as the likelihood times the prior and divided by the marginal. And again, I hope without any formal definition derivation, you should now realize that the posterior of that is now written as this, which is a kind of readjusted Dirichlet distribution. Okay, where are the readjustment? You have the alpha minus 1, which is the original component in that Dirichlet, and you have the k, the nk, which is what? Which is the actual observation of the number of times that case event happened in your real data. And therefore, your posterior is now a reflectance of the joint influence from the data and from the prior knowledge. Okay? And here we want to again point out to you that this Dirichlet is known as a conjugate prior, because if you look at the shape, the form of the prior distribution and this posterior, they are symbolically equivalent. They both have this product of dimension-specific probabilistic distribution lifted to the power of some weights. There is a prior weights. There is a count of that dimension. Okay. All right, and sometimes people are not totally satisfied with having just a posterior. They want to have a more handy kind of estimation for other operational reason. And one of these estimator is called the posterior mean estimation. You just compute the mean of the theta under this posterior distribution. So that basically needs you to take expectation over the theta. And imagine you know how to do the calculus in here. You should be able to, derive a closed form estimation of the posterior mean, which is again a very natural estimation. So in here you have on the denominator the real counts plus the prior weights of that particular case event, and then in the denominator you have the total counts plus the total weights of all possible events. That's why people call alpha k to be the pseudo counts. It's the imaginary counts you had in your brain from your prior. Okay? And here are some facts that I'm not going to go through, but you can basically hopefully remember how the Dirichlet distribution can be manipulated. For example, computing this normal constant can be quite non-trivial if you really want to do the calculation, but here is a way to help you remember that. Okay, you can compute in closed form the normal constant from a bunch of gamma functions. Gamma is defined by a factorial of the argument, and here you have the product of gammas over every hyperparameters, and here is gamma over the sum of all the hyperparameters. Okay? Hopefully it's easy to remember. Once you know that, you actually can be more comfortable in dealing with all these posterior and prior transformations. And you can compute this marginal likelihood in a much more easy way. All right, I think we can pass that. And I think these are all pretty straightforward facts. Any questions regarding all this little mathematics that I don't have a strong desire to present? Unless you have any questions. Yeah.
Sorry, I think
Yeah.
it's just because it's really should be a positive n, right?
It should be a positive n where?
In the posterior, it should be alpha k plus nk.
Here?
In any of the theta to the power of the long expression.
I don't know what I'm talking about. Which?
Theta to the alpha k nk minus 1. Anywhere that shows up.
Oh, here?
That should be a plus, yeah?
Oh, it should be plus, yes.
Okay.
Yes, thanks. Good. That means you really understand what I'm talking about. That's great.
I think it is. It's just hard to see.
Oh, it's very strange. Actually, on my screen, I see positive. Somehow, that bar is lost. Anyway, yeah, I was surprised I can make that mistake. But anyway, thanks for pointing out. Yeah, it should be a plus here. It should be on your slides as well. Any other questions? All right. So maybe one more thing worth pointing out is this so-called sequential Bayesian updates. Because now, suppose that you are in a scenario where your data is not giving you, in a single deposit. You are constantly receiving new deposits of data. What do you do as a Bayesian? Well, the naive thing, of course, is that today I receive a data deposit. I perform a Bayesian estimation. And tomorrow I had a new deposit plus my today's deposit. I should redo the whole thing again. That's probably a naive way of doing that. But it turns out that you don't have to do that. Because of this conjugacy, you will see that the posterior distribution, okay, is dependent on data and the hyperparameters in a very unique way, to the point that you can just update your posterior by just adding this new data sufficient statistic into the estimator, okay, without redoing the whole thing. So there is one more puzzle that I think I want to touch bases. But before I mention that, are you already having some doubts in what I'm doing here? So do you feel a little bit puzzled about where does this alpha coming from? Okay. Alpha are known as the hyperparameters in the Bayesian prior. And where should we get them? That's actually a good question to ask, right? So this slide actually answers partially about that puzzle. Okay. In the easiest case, you can guess the alpha. Okay, you basically say, I want the Dirichlet to be so on and so forth. And that's actually what people often do before they have any knowledge. And the function of the alpha becomes a pure technical one. Say it's smoother, so that you don't get a zero posterior on any dimension, even if you don't see any counts of that event. Right? You put a kind of vacuous 1, for example, on every alpha. Remember, alpha is a vector, right? So you can do that. But what if you are going to share your knowledge with a collaborator who actually, say, for example, you are fitting, let's say, a topic model over all the articles collected from Nature. Okay? Then your friend want to do his estimation from the articles in Science. Okay? So what should you do? You can, of course, say, I'm not helpful. Do your own stuff and just hope for the best. Or you want to be helpful, then what do you actually do to him? I bet one thing is that you can just give your data to him. Say, I double your data. You can mix your Science article with my Nature article, and let's do things together. But that's a little bit strange, because the topic model learned at the end of the day isn't really satisfying his utility, right? So here is another way. You can basically use your Nature article to learn the hyperpriors, okay, of those Bayesian prior, or the coefficients, and then you give him those alphas so that he can treat your information as a prior. What is the good thing about prior? Prior is a soft constraint, if you remember, right? It's basically generating a kind of a trade-off between your real data and your existing knowledge. If the real data are really very, very rich and in large quantity, you can erase the influence of the prior. But otherwise, the prior will generate a substantial effect. So that's kind of a more flexible way of giving him the data to retrain the whole model. So therefore, there is an incentive of learning the alphas, using data. And this is known as an empirical-based estimation. Okay, you basically can now write down, a likelihood function, which is not defined on just the original likelihood model, but a Bayesian model with this theta, the original parameters of the distribution, being marginalized out, because they are now treated as random variables. Okay, therefore, actually, I should write maybe a little bit more here. This P equals to integration of we can do that. Okay. And how this can be happening? Well, we can use the fact that conjugate prior leads to a closed form integration of this marginal likelihood. Therefore, you can actually get them out in a closed form. So there's a big literature of doing this in a very data-dependent, model-dependent fashion. But I just want you to know such technique exists. And if you need that, you can look the book and check the derivations in here. All right. Yeah.
So if you already do all this stuff, estimate alpha, it seems you have to do everything that you can do with this graph. So what's the point of after this?
What's the point of what? What is your question? I mean, I wasn't catching that.
If you already estimate alpha using this MLE, it seems you have already know the structure or the theta and stuff.
Yeah, and then we call the graph model is learned.
Yeah, already learned. So you already learned that graph. So
Yeah, that's true. Yeah.
this graph is useless after you learned it.
Why? If the graph learned is useless, the whole point. Why do we want to learn graph? I'm a little bit puzzled, right? So you first you want to say I want to learn a graph. Then I say it's learned. Then you say it's useless. What's the point in here?
I want to learn the theta here. Yeah. So the theta is sampled from alpha. And if I already know the alpha, I can directly sample theta from the alpha.
There's data as well. How can you direct sample?
But when you do MLE, you already consider the impact from the.
You cannot do two things. In this same graph model, you do MLE or you do Bayesian. You want to use these two things to solve the same problem. You have to stick with one thing.
Do MLE, there's no point to do the kind of the Bayesian.
What if I don't want to do MLE? I want to do Bayesian? If I already want to do MLE, then I don't even need to have that. I don't have that graph. This is a Bayesian graph. Okay. Once you write down this graph model, that means you want to do Bayesian.
So you mean you first estimate alpha, use the MLE, and then take that alpha.
That's MLE on a different model. It is MLE on this model, not on this model. Okay.
But it still seems a little bit roundabout. I mean, if you're uncomfortable with getting a point estimate for theta, here you're going to put a hyperparameter
Yes.
point estimate for alpha by marginalizing out theta. In a sense, you're kind of reparameterizing your distribution in terms of alpha. And so if you were uncomfortable getting a point estimate for theta, I think you should also be uncomfortable getting a point estimate for alpha.
Yeah, that's why this is not a Bayesian estimator anymore. Okay, once you do empirical Bayes, you're already a frequentist. Okay, you do want to get a point estimation for information transmission, basically. The other way I want to use your knowledge, and this is a typical frequentist attitude. I give you a point estimation of something, right? And once you are into another domain, remember, in the other domain, this guy is borrowed from somewhere else, and this is unknown. This is new data. Then you are now estimating this under your new data and a alpha coming from elsewhere, right? Any other questions? In fact, that's the point of doing the project. Once you are in the project, you will actually run into all these issues, and you will figure out actually how the dynamics are coming through. You have multiple data sets, and you may actually want to make the usage of data sets in a flexible way, getting knowledge from here and moving to there, do transfer learning. This is a typical of transfer learning, in fact. Okay. All right. And here I want to also just flash at you some space in choosing different priors. We used this called Dirichlet prior. And you can probably see already that Dirichlet prior has a kind of a specific flavor in how they look like. It's kind of symmetric, right? And therefore, they cannot capture some more complex kind of distributions over the theta. For example, what if two particular events likes to co-occur more often than others? Right? This kind of correlation. And that's actually not possible in Dirichlet. And so here I have another prior that you should know, which is known as the logistic normal prior. It's actually a normal distribution. Okay. Basically, I define a mean and covariance in a Gaussian fashion over theta. But this is problematic because a Gaussian distribution generates a variable which is it can be positive and negative, right? So how can we use that number to define a probability? Okay, transformation. You need to do a logistic normal transformation. You want to actually lift it to the exponent, and then you normalize it. Okay, like this. Okay, you sample this theta from a logistic normal means that you need to first sample auxiliary random variable gamma from the normal distribution, mu and sigma. Okay, and sample not all of them, but only k minus 1 of them. And then you are going to build the theta based on this transformation so that your theta is guaranteed to be positive and norm to 1. Okay. And so this is a very flexible thing. It gives you actually a weird shape like this. You can see the correlations between dimensions. But unfortunately, this is not a conjugate prior. Therefore, you are going to run into some algebraic issue in deriving the equations for updates. And we are going to skip the technical details in here, but if you are curious, there are quite a few papers just flash at you the equations of this derivation. Okay? And one of the paper from David Bly on topic model known as a correlated topic model is exactly using this kind of logistic normal to do the prior distribution over the topics. And we are going to discuss that later when we study topic models. All right. So I can tell the same story again for parameter estimation for continuous random variable. But I think we are quite familiar with that already. I'm going to skip that. And remember, the whole story about Bayesian estimation, about sequential estimation, and the Bayesian setting for parameters all carry over from discrete to continuous. And here I prepared, hopefully, enough kind of facts for you to remember. Okay, which captures, treating, the mean as a variable following a prior, treating the variance as a variable following a prior, or treating both as a variable following a prior, and they all have their proper conjugate priors. And you can find their names in the slides, something called a gamma distribution, or a normal distribution, and so on. But I think the name isn't that important as long as you understand the principle. And here are some interesting properties of a Bayesian estimation over the mean and the coefficients. And the key message I want you to remember is these two equations. Okay, under a Bayesian estimation of the Gaussian mean and the Gaussian variance, the mean becomes a convex combination of your sample mean and the prior mean. Okay, and the weights is defined by both the variance of the prior, the variance of the likelihood, and also the number of examples you observed. Likewise, the theta, the posterior distribution, the variance of the posterior distribution under normal is also a combination of the prior variance and the distribution variance in this way. Okay, And this curve shows you the influence of new data. The more data you observed, the more it will be shifting the mean to its sample mean, and the less variance it will result in. Okay, just to basically making this term dominant over the other term once you have more data. All right, and I have many other scenarios where the mu is known, but the variance is not known, and you have a gamma prior for that, which is also a conjugate prior. So this kind of facts is very useful if you want to do tricky modeling for Gaussian distributions, but we are going to skip that for the technical presentations in the class. I do want to actually move into some bigger picture to see how the whole story can be put together to estimate Bayesian network. So here, another slice is now lifting you from the single node density estimation to an estimation problem of conditional density, which is this child given parent type of building block in the Bayesian network. Remember, the Bayesian network is made up just these two components. One is the marginal likelihood, the other is the conditional likelihood. And again, in last lecture, we said that all the interesting or practical conditional likelihood can be treated as a member of the generalized linear model. And we know actually how to do MLE and Bayesian estimation in that setting as well. I have some supplementary material at the end of today's lecture slides so that you can see some real examples. Okay? So having that, we are now here. Okay? Sorry for the fast speed, but now we can see the whole graphic model being like this. It's made up of a number of such local conditional property distribution and a marginal at the root of the direct graph model. And your likelihood now is a sum of all the log components. And sometimes the graphic model can be written in a more kind of succinct way because there are repetitive structures in the graphic model, which we call plates. So sometimes, if we see a graph like this where multiple instances are drawn from the same distribution, we basically put a plate and put a number here to indicate how many copies are drawn from. And that basically translates to this particular definition of the drawing likelihood, where all the components are multiplied together, just under the ID assumption. Okay? So with that, now the estimation problem is formally decomposable into these different pieces, and therefore estimating the parameterization of a full Bayesian network is equivalent to estimating the marginal likelihood, marginal density, or the conditional density of all these component graphical models. And again, this assumption only holds when the whole graphic model is observed. We're going to talk about issues when some of the nodes are unobserved, and that's actually a story we're going to tell in next lecture. Okay. So everybody know how to do this? We actually spent the previous half lecture actually talking about a few instances of that. So just try to get those techniques applied here. And you will see something like this. Every time you are going to estimate a local table if the variables are discrete. And here, I just give you an instance about a particular multi-way table, which involves counting child event conditioning on multiple parental event. So one thing that is a little bit tricky is how to define priors in a whole graphic model. So we learned how to define priors already for a single density estimator or for a two-node conditional density estimation. But what do we mean by defining a prior distribution for the whole graphical model? Okay. Why it is tricky? Well, one way of defining the prior, we actually have this graphical model, x1 to xn, and the given g and theta, right? And the trivial way of defining a prior is to write, let's say, p of, just define the prior for the parameter, for example, and we can do that. So in here, although symbolically they look no different from the Dirichlet and other things we talked before, but in here, this theta is not just a multinomial. It is all the parameters you use in the graphic model. They have a lot. Maybe, for example, they are 10 different multinomial distributions, okay, in different places. Then what do we mean by writing a prior for that? Okay, actually that involves some very sensitive issue. If I write a prior such that it is defined jointly over the entire vector or collection of parameters so that they cannot be break into pieces, then my maximum likelihood estimation for a graphic model can be very difficult, because I rely on the fact that once I define a log likelihood here, I can turn these big pieces into smaller pieces so that I can invoke a local estimation rule. But if this guy does not decompose, I cannot use any local rule anymore, right? So therefore, defining a parameter prior for an entire graph model has to follow certain rules. And these kind of rules were discussed in detail in Geiger and Heckermann's paper a long time ago. They propose that you need to make a few assumptions, okay? The most important assumption are these two pieces, which actually critically influence how can you perform efficient estimation. One is the so-called global parameter independencies, which means that if you have different nodes, okay, each have their own parameterization, your prior should make sure that they actually decompose over different nodes. Every node should have their own kind of prior distribution, okay, which is not coupled with a prior for the other node. Okay, that's actually a so-called global parameter independencies. This is kind of natural, right? You kind of already realize that you can probably say, okay, I will put a prior here, maybe, and I will put a prior here so that I can make an explicit graphical illustration of global independencies. The second independencies is very subtle, and you should remember. When you actually parameterize a local conditional distribution in here, you actually need to have multiple distributions, because depending on the configuration of the parent node, you actually will be looking into different probabilistic distribution to define the likelihood of the downstream event, right? Therefore, for every of these parameter or parental configurations, you need to define the configuration-specific prior. Okay, that's called local parameter independencies, which is expressed in here, right? So, this parameterization is unique for a particular configuration of the parent and of the child of a node and their parents. Okay, and in particular, even if they look like the same prior, depending on the parent being one configuration or the other, these two prior distributions should be independent of each other. Okay, so with that kind of setup, now you are safe to write down the whole joint likelihood and still decomposable into local terms, so that each of these prior can be grouped accordingly with their local kind of parameters and local variables that you need to use for the estimation. Okay, so this is something I want you to take home. Very subtle, but this paper actually explained the whole thing very nicely. So at the end of the day, you are going to have a graphical model like this, right? You have the observation in here, and here you have two parameters, okay, here and here, and they must be independent of each other, okay? And then for parameters for two different configurations of the parents, for example, here x1 is the parent of x2, they can have one or one complement, then these two parameters should also be independent of each other. That basically guarantees a global and local independencies. Then you have the factorization rule carrying through. Okay, that's the first thing I want you to remember for global graphical model parameter estimation. And what are the distributions that can be used to define such a likelihood, such a prior, which enjoys global and local independencies. And here, Geiger and Heckerman provided a few proposals. For example, this derivative prior can be a safe one. You can use the same dish prior to define, the prior for this variable and that variable in different parts of the model without worry they being coupled. Okay, and for Gaussian distribution like this, you can use something called a normal prior if you only want to define priors for the mean, or you use something called a normal weight-shared prior, in which the mean is defined by a normal, and the covariance is defined by this weight-shared distribution. Okay, so these two are choices where once you use them to generically for the prior on any parts in the graph model, they still guarantee global and local independencies. Yeah, you have a question? Okay. All right, so the second element I want you to take home is some kind of reduction of the modeling expenses. So here I have, this actually technique is called parameter sharing. Actually, maybe I will draw another example which better illustrates that. Suppose I have a HMM, if you remember. HMM is like this. Right? So on every of this edge, I can basically define a distribution of p x I given x minus t minus 1 at t. And at every different t, I can have the same thing in like this. Right? So they could be totally different distributions, meaning that in my first toss, second toss of the dice, I'm going to follow my previous outcome in a certain way. But in my third toss of the dice, I'm going to follow my second one in a different way. That's possible, right? But if that's the case, what would be the parameterization cost, and how are you going to learn that? If I want to treat this A, let's use the A as the shorthand of that transition probability table. I need to have a A1 here, a A2 here, and a A3 here, right? That's basically a pure, kind of canonical graphical model way of parameterization. On every, local child and the parent combination, I have a separate local conditional distribution. Now the question is it necessary? Or if we do this, how are we going to train that? Okay, in this case, how are you going to learn the A? Remember, learning the parameter needs to have data. And so what do we expect the data to look like in this case, if we really meant to use it for learning the A's? Remember, we need to have something called IID data. You need to have multiple copies of that. Otherwise, you don't have a sufficient statistic of the events for estimating frequency, right? So that means in your training example, you need to have multiple runs of the dice, or multiple instantiations of the choices of the dice. And then you're going to do an alignment. You're going to say, in the first step, first window, I saw such event, such event, such event, many. And then you're going to count in my first step how many different combinations happens, right? And the second window, you're going to do the same, which is not necessarily a realistic idea, because you may just go to the casino once, and you get only a long sequence of the whole thing, and that sequence wouldn't be repeated the second time with the same distribution, right? So in that case, what would you do? Okay, so here the idea basically of a parameter sharing is going to kick in, right? You are going to make a reductionist assumption that at every transition, I'm going to follow the same A, so that A is not going to be repeated over different data instances. It is going to be repeated within a data instance of repetitious events. Okay, so this is called the parameter sharing, which means that you can have another layer of reduction by placing the local conditional distributions in different places of the same graphical model. Okay, especially if the graphical model structure is repetitious or redundant over the space of graph. Okay, so with that, now you can see this definition of the joint likelihood. It is going to be, even for a single observation sequence 1 to t, you now have a product, but the product will be now using the same A, okay, over different instances. And then if you have multiple instances, you can have another outer summation to actually further enhance the observation. But even if your n equals to 1, the estimator can still be performed. Okay. All right, so that's another idea, parameter sharing. And under parameter sharing, these are the solution, and you can, following the same kind of Bayesian idea, you can introduce a prior like this, okay, and call them to be shared across different. In here, actually, what I meant to say is the following. So this graph shows what? It shows basically a prior that only satisfies something called the local independencies, because globally you are going to share the same parameter, right? Therefore, you only need to have one kind of instance of the A. But depending on different configurations of A being used, this A is a matrix, right? It's basically defining the conditional probability of transitioning to the next event, given the first event. The first event can happen in many different ways, and each way actually corresponds to a table, corresponds to a row in this table, right? So this is also known as a stochastic matrix. And to define a prior, you can basically use a single prior, which can be shared by multiple different rows. Okay, and to ensure this prior is locally independent, you are safe to use a Dirichlet prior because they actually have this kind of nice property. Okay, so with that, now your estimation of these numbers in the transition matrix can be made very straightforward. What you need to do is just to do counts of adjacent events in all possible configurations. You basically are going to examine all possible transitions in the same chain and across different chains, and just count how many times a transition from I to J happens. Okay. Then you also count how many times an event began with a I, and then you put these coefficients, which are the pseudo counts, in your prior distribution, and you get an estimator. Okay. And in fact, you can also write it in a tricky way to expose the fact that a Bayesian estimation is a trade-off between the MLE and a Bayesian prior knowledge. In a convex combination fashion, you have this MLE estimator, and this is the prior weights. Okay, I think here are some examples in HMM which you can go through at home, but at the end of the day, we have the following summary. Okay, so the take-home message is that learning fully observed network based on a log likelihood function is easy. Okay, it can be decomposed into sum of local terms, and then based on that decomposition, you can often turn the global search problem into a rather local search problem or local analytical solution. And in structured learning, that actually motivates the Chow-Liu algorithm. And in the parameter estimation, we have these typical scenarios that make use of generic laws of dealing with expanded family distributions and the generalized linear models. Okay, I think that's all for today. There are some, auxiliary informations full of equations and instances. You can go home to find out how specific estimations can be done. Question there?